I wish. Yeah, you can see the credits down here. Yeah. All right, so I still see a few people out there, so I'll wait a little bit longer before coming in, or before really starting. Yeah, just start? All right. All right. Too bad for everyone else starting. Okay, so I'm going to be talking about the universe machine. That's a new empirical model. We finally submitted the paper, so those of you who have heard me talk about it for many years, it's finally on the archive. You can read it, and I'll just overview a few of the results. Thanks. All right, so is this, can everyone hear? All right, good. So I'll just overview a few of the results here. And just as a very brief introduction, what is an empirical model? An empirical model is something that all of you know and love and use every day. And the classic example is actually cosmology. So for instance, omega lambda and omega matter, we can't derive what these are from first principles yet. We don't know what dark matter is. We don't know what dark energy is. We don't even know the equation of state for dark energy. But based on our adoption of a common framework, a common parameterization for how should the universe evolve, then we can start making observations that constrain this parameter space. And by combining many different observations, we can get a very tight constraint on what the actual evolution of the universe looks like. And empirical models for galaxies that I do the same thing, except instead of omega lambda and omega matter, we parameterize how galaxies form in dark matter halos. And by combining many different observations, we obtain very tight constraints then on what the galaxies are doing in dark matter halos, as opposed to how the universe is evolving with time. Okay, so introduction over. What do we know about galaxies, and specifically, what kinds of physics can we constrain about galaxies that we can then use empirical models to resolve? So the star formation rate of a galaxy, we know from previous work, mine as well as many others, we know that the star formation rate of a galaxy depends on its host halo mass and the redshift, such that as you go early and earlier in time, then the star formation rate in the fixed halo mass increases. And also as you deviate up or down from the Milky Way's halo mass, then the efficiency of star formation goes way down. So we've known that for some time. What we've also known for some time is that the star formation rate of a galaxy also depends on the halo assembly rate. And so just as an example of this, in clusters, the satellite galaxies, of course, are typically more quenched, as opposed to if you go in the field and look at isolated galaxies. And if you ask what's happening to the dark matter halos in the field, isolated halos tend to be accreting matter, and it's very rare for them to lose or not have any accretion. So that includes both dark matter and baryons. And the satellite halos around these satellite galaxies in clusters, by contrast, are getting tidally stripped. So they're losing matter, have negative accretion rates. And so what this goes to say is that the accretion rate or loss onto the dark matter halo hosting galaxies is correlated with the star formation rate of the galaxy. So even though there may not be any causation, if there's a correlation, we can constrain what that correlation is and then use it to understand better the connection between what galaxies are doing and what their host halos are doing. So that's the approach that we take here. And so the universe machine model, we start with the dark matter simulation that gives us halo properties as a function of time, as well as merger trees. So a merger tree is, of course, the assembly history of a halo, including how it grows in terms of its most massive progenitor, as well as everything else that merges in throughout the history of the halo. And what we do is add on top of that a minimal galaxy formation model. And that is just that the star formation rate of a galaxy depends on some halo properties, which are the mass of the halo's mass accretion rate, and the redshift. And I'll get in a bit to how we constrain what this function looks like, but if we just adopt or take a guess for a moment at what this looks like. Any choice for this function gives me a way to assign star formation rates to every single halo in the simulation. And if I then integrate over the mass accretion history and merger histories of halos, I can convert those star formation rates into the stellar mass and colors and luminosities of the galaxies that should reside in the center of any given halo. And so that means I've calculated the galaxy properties for every single halo in the simulation at every single redshift. And so for any choice of what this function looks like, I can create a full Mach universe like this and observe that Mach universe, repeat the last 30 to 40 years of astronomy, compare that with real observations, and that gives me a likelihood function. It tells me for any choice of this model, how likely is it to match the statistics of the real universe? And then I feed that through an MCMC algorithm to infer, based on real observations, what is the allowed range of physical models that can then reproduce what galaxies are doing in the real universe. And the beautiful thing about this, you might recognize a lot of similarities between this type of machinery and semitic models. But there's a fundamental difference, which is that I don't put physical priors on what this function looks like. And what that means is that what I'm using is all the observations we've collected over the past decades that constrain what are the physics that's driving galaxy formation in halos. And it's an amazing statement that we have so many observations that it doesn't matter what priors or not I have put on this function, but the observations are sufficient to constrain very tightly what are the allowed models that I can put here and still get statistics that are consistent with the real universe. The other very beautiful thing about that is that if I don't have to put physical priors, if I don't have to put in my own prejudices for what this function looks like, then I can let the universe tell me things that I didn't expect to see beforehand. And that's very nice. Okay, so just to say a little bit more about the parameterization that goes in, we could, of course, adopt a three-dimensional grid for this, but that's a lot of parameters, so we have a smooth parameterization to cut down on how many things we have to constrain. And so if we just talk about the parameterization for a moment, we have a star formation rate as a function of halo mass and redshift and mass accretion rates. And functionally what we do is, in a bin of halo mass and redshift, we have some quenched galaxies, we have some star-forming galaxies. And we have a knob to control the correlation between halo assembly rate and galaxy assembly rate. And so if that correlation were turned up to unity, then that would mean we'd put the most star-forming the most star-forming galaxy into the most rapidly accreting halo in that mass bin and redshift bin, and the most quenched galaxy into the probably satellite that's most rapidly losing mass. But we can control that correlation, we can dial it down, and add some scatter between the galaxy star formation rate and the halo assembly rate. And the observable that really constrains this most is the correlation function for quenched galaxies versus star-forming galaxies. Where that comes from is that satellites, which are rapidly losing mass, are much more clustered than field galaxies. And so if we have only the quenched galaxies going into satellites, then you have a much higher difference between the quenched galaxy correlation function and the star-forming galaxy correlation function. So over the widest redshift range and mass range that we can get data about correlation functions for star-forming and quenched galaxies, then we can increase the knowledge that we have about the correlation between galaxy and halo assembly. Okay. So going on, I wanted to show you a movie of what one of these Mach universes looks like. So this is a fly-through of redshift 0. So galaxies are populated in the Bolshoi-Planck simulation. I guess I could turn this. Oh. Yeah. So galaxies are populated in the Bolshoi-Planck simulation, and then we're flying through the redshift 0 Mach universe. And the point of showing you this is not only to say that we can constrain, we can use data about galaxy number densities and star formation rates, but we can also use spatial information, like what are the correlation functions, or cross correlations with dark matter, like what's the weak lensing, or any arbitrary, more complicated statistic, like group catalogs, or any crazy measure of environment with galaxy star formation to understand better what is the connection with galaxy star formation rates and halo assembly rates. And if you recall from cosmology, the more different observables that you can combine together, then the more, or the better the constraints that come out at the end of the day. So this obviously is a lot of work to generate a Mach universe for every single model. But if you recall what I said earlier, the star formation rates that we're putting in are a very simple model of halo, or a very simple function of halo properties. So halo mass, mass assembly rate, and redshift. And what that means is that it's embarrassingly parallel to evaluate any of these models to generate a Mach universe. And so we get extremely good scaling even to the largest machines that we've run on. So that's perfect linear scaling with a number of processors. Getting back to the science, the data that we can then synthesize to make constraints on galaxy formation and quenching So things that we could use before include like stellar mass functions, number densities of galaxies, specific star formation rates, cosmic star formation rates. But now we're adding in quench fractions of galaxies as a function of stellar mass and redshift. We're adding in correlation functions split by star formation status, whether it's star forming or not. To higher redshifts as well, we're using luminosity functions at redshifts 4 through 10, UV luminosity functions. We're also including things like central quench fraction as a function of environment. So we're including a lot of data to get at what is the physics driving galaxy quenching. Why did it take so long? Many of you have heard me give a talk like this before. When you have so many different data sets, some of them are bound to be inconsistent with others. And so, for example, many of you are familiar with, at redshifts 4 and above, there's a huge diversity in stellar mass functions. And what do you do about that? Which one do you choose? And so what we ended up doing, Appendix D out of J, was I wrote a new SED fitter that would take into account physically realistic star formation histories that were consistent with the evolution and luminosity functions, so we could get better stellar masses from redshift 4 to 8 by refitting to Kendall's SED stacks. So that's one thing out of many that we had to do to make all the data sets consistent. And so one of the nice things, or like usable things about this paper, is that we include a lot of data that we've very carefully worked through to get out the inconsistencies. So we can get a self-consistent result as opposed to results that are telling us very different things about what galaxies are doing. Good, so actually moving on to the results, of course we got new relationships for the stellar mass to halo mass relation. I just want to comment briefly that at redshifts 4 and below, this seems to be fairly constant or unchanging with time. At redshifts 4 and above, then the result that we get seems to favor increase in the stellar mass halo mass relation as you go to higher redshifts. But if you look at the error bars, they're large enough that you could still, with current data sets, mostly fit the data if you had a fairly consistent relationship. And so this is something really that we won't solve until James Webb flies and we get much better stellar masses and potentially with clustering halo masses. Why should you use these new stellar mass halo mass relationships instead of the ones that you've used before? I feel like a new car salesman, but one thing that changed between 5 years ago and now is, of course, Planck, and so we have new cosmology, and that means we have more halos at high redshifts. So the increase in omega matter from WMAP to Planck means there are a lot more rare objects, basically, and that includes at high redshift the number of halos. And so if you compare the old results, what happens if you switch the new cosmology, then you get a different stellar mass halo mass relationship at high redshift. So that's important if you're running a simulation and trying to calibrate to the stellar mass halo mass relationship if you're using Planck cosmology. Another thing that's different is if you look at redshift 0, there are two differences. So this purple line is the new results. You can probably barely see it. This sort of red dashed line is the old results from 2013. Now we include much more stellar mass in massive galaxies to reflect that, say, stellar mass functions like the Bernardi stellar mass functions typically now include more of the light that was previously called intracluster light into the central galaxy. And we also have a difference at low masses, which is that previously we thought that there would be a large correction from surface brightness incompleteness in the stellar mass function, and the evidence for that has not continued to suggest that there is such a thing. And so then the low mass slope changed quite a bit, and that's a lesson for people who like to extrapolate, that you shouldn't always take the low mass slope too seriously and extend it down to however many decades in halo mass. We also, of course, have new star formation rates as a function of halo mass and redshift, and the major differences from 5 years ago is that we have a much better understanding of quenching in massive halos, and so then, of course, the star formation rates have gone down for massive halos. We also have constraints on what's the correlation between galaxy and halo assembly that I mentioned earlier. These come from correlation functions. And we find with very high significance that there is, in fact, a correlation between galaxy and halo assembly, but also that it's not perfect. And so there is uncaptured stochasticity either internal to the galaxy or from some halo property that doesn't correlate with assembly history, like the one that we're using, that explains some additional amount of quenching or star formation in galaxies beyond what we can fully predict deterministically. Going to quenching, what causes quenching? This plot, I think, summarizes a lot of the history of the universe, what's happening. So on this axis, I have halo mass. On this axis, I have time since the Big Bang, or if you prefer, redshift up here. What I'm showing with the colors is the fraction of galaxies forming stars. And so down here, it's nearly 100%. These yellow colors are 100% star forming. The black colors are 100% quenched. And you see across most of the history of the universe that there's a fairly sharp transition as you go up in halo mass between star forming and quenched. So the halo mass over much of the universe is driving quenching, or at least correlated with quenching in galaxies. And as you go to lower redshift, then you have more satellite galaxies, and you start running into stripping, either tidal stripping or ram pressure stripping, that's driving quenching in satellites, and therefore lower mass halos at low redshift. Diving into this a little bit more, we can ask, how do these predictions compare with increasingly complex models for how, theoretical models for how galaxies quench? So what I've shown here is, as a function of redshift, how does the halo mass, where the quench fraction is 50%, how does that change with redshift? So here, at redshift 0, about 10 to the 12, so basically Milky Way mass, half the galaxies are star forming, half the galaxies are quenched. And that halo mass increases very robustly as you go to higher redshifts. If I just compare that with a model where galaxies quench above a constant threshold in virial temperature, then that would be the red line. And so you'd find actually that it would be easier to quench instead of harder to quench halos as you go to higher and higher redshifts. And that's just going to say that as you go to higher redshifts, the virial temperature at fixed halo mass increases. And so it becomes easier to quench. So that's obviously ruled out. If you consider a different model where you have a constant threshold in the cooling time relative to the dynamical time of the halo, or equivalently relative to the age of the universe, that gives a prediction of a flat threshold in quenching as a function of redshift. And while that may be the case up to about a redshift of 1 or 1.5-ish maybe, it doesn't seem to be matching what we find at higher redshifts. And so it's actually somehow easier to form galaxies as you go to higher redshifts. And the last model that we compared to is, of course, the Declan-Birnbaum model about cold flows penetrating hot halos. And there what we find is that actually this flatness and then starting an upturn at around a redshift of 1.5 is actually very similar to what we see. But then the slope is different here. And so actually I would call it a success that there is some prediction about where the inflection happens, that there's different physics coming in. But then the question about what is the slope, what this might be saying is that there's different physics that's relevant, for instance, black holes, which were not considered in the Declan-Birnbaum 2006 model, that may make it harder for galaxies to form in massive halos than just the cold flows alone would have suggested. Also, I wanted to talk a little bit about low redshift and satellite quenching. So one thing that was really surprising for us is that being a satellite only mildly increases the quenching risk. And so what I'm showing you here is the quench fraction of galaxies as a function of stellar mass split by whether they're satellites or centrals. And so the absolute numerical difference between these two is never more than 30%. And that was surprising to me, at least, because probably like you, I've seen many of these images of clusters where you have a lot of quenched galaxies. But then, of course, we have to remember the selection effect. Where are these images taken from? And the most visually appealing images, of course, come from cluster centers, where you have a lot of galaxies. If you go out just a little bit to 0.1 times the virial radius, here's showing you the full extent of the halo radius in Sloan. If you go out to 10% of the virial radius, then you immediately start picking up star-forming galaxies. And all that's saying is that whether a satellite gets quenched or not is dependent on its orbit. So if it's just orbiting in the outskirts, it's not such a harsh environment, and you can still have a lot of star-forming galaxies. But if you have a very radial orbit and you go right through the center of the dark matter halo, then you experience much stronger forces, much stronger stripping, and you quench much more rapidly. So forging ahead, because I don't have a lot of time, there's a lot of data, of course, in the paper, but then also a lot of data that we've released online. So if you go to my website, if you go to the data section, you can find all the data and all the plots in the paper. So that includes the statistics for, say, stellar mass-halo mass relationships, a lot of other things that I'll briefly flip through. You can also download the observational data constraints that we've compiled, as well as catalogs, including star formation histories, as well as light cones for all the candles fields you can download. So I just want to walk you through very briefly what's available. So as I said before, we have star formation histories, so catalogs for every halo in Bolshoi-Planck. What are the star formation histories for the best fit model? We also have pre-computed stats. So for instance, what's the star formation history as a function of stellar mass or halo mass in redshift split by star forming and quenched. We also have, say, fractions of stellar mass from mergers, or basically in situ versus ex situ star formation, predictions for correlation functions and weak lensing shears as a function of redshift, stellar mass spin, and so on. We have, say, distributions of satellite quenching times after they fall in. And of course, we also have open code. And so all the information that I just showed you, you can download the code. You can do a full analysis yourself. It's not that we've restricted any part of it. You could rerun the entire analysis if you wanted to, or add on new modules to calculate new things and include new data constraints. And it's even documented, which is special. So this documentation includes not only what data we provide that we've already pre-calculated, but also if you want to, say, calculate your own light cone, if you want a different field or a different size or whatever, then it explains how to do that. So we've made a lot of things public. We want people to use this because it is really a lot of work on our part, and so we want that work to be beneficial to other people. And just in the last minute or two, I want to say a word about the future. So all of this was combining physical constraints on galaxy formation. So how do galaxies behave as a function of stellar mass and star formation rate? And as you all know, stellar mass and star formation rate, and often redshift for many galaxies, is not a direct observable, but it's dependent on assumptions that go into the SPS modeling, the Behroozi codes, the dust, and the metallicity models. And so even though we calculate in restricted cases, say, UV luminosities for galaxies, the models that we're using for dust and metallicity are fairly primitive in the current version. And so in the future, what we want to do is go directly to the full n-dimensional distribution of galaxy luminosities and colors. And where available, of course, absolute luminosities from spectra. And by doing this, we hope to get around some of the inconsistencies in the data that come from using different photo-Z codes, that come from using different SPS models and assumptions that go in. So we can derive a physically self-consistent picture of galaxy physical properties, stellar masses, that are constrained only from the galaxy's luminosities, as opposed to then assumptions that have gone in. And we hope then, by doing so, to recover not only galaxy stellar masses and star formation rates, but also our current uncertainties in dust, also our current uncertainties in metallicities that come even after combining all the available observational data that will help us understand what kinds of observations we need to do to resolve any remaining degeneracies. So with that, I just want to say thank you and ask for any questions.
Questions?
So I'm sorry if I missed it, but what do you define as forming stars in this plot and in your other plots?
Yeah, so for this plot, forming stars is above a specific star formation rate threshold of 10 to the minus 11.
Okay.
But when we compare to data sets, for instance, many data sets are UVJ colors to decide yes or not. We do apples to apples. So we compute the UVG colors, and then we ask, did it land in the quenched box or not, when we compare with the observations.
Okay, so I guess I'm curious then, because more recent observations of like BCGs find that they're often star forming, like 50% of them are star forming at redshift 1. So how would that, it seems like that's very inconsistent with this picture.
You'll have to tell me about those data sets, and we're very happy to include them.
Cool.
I probably said, but like, so when you take the relations that you were saying, or really, I guess my question is like, how do you account for the scatter in the relations when you put this into your like universe machine, and sort of related to like the abundance matching thing. So at what redshift do you think it starts becoming a little bit less reliable?
Yeah, so let's see if I can go back. So first question is on the scatter. So here, so we have scatter arising from two reasons. One is diversity in halo merger trees. And so different halo merger trees will assemble earlier or later. And that will give us scatter in the galaxy properties. But of course, we also introduce some scatter here. And so that means if we don't have perfect correlation between halo assembly and galaxy assembly, then we also have some internal stochastic scatter that we introduce. And so then the other question was about abundance matching. And I just want to take this opportunity to say that although abundance matching grew into this type of modeling, the relationship is between abundance matching and empirical modeling today is more like the relationship between caterpillars and butterflies. So even though it grew out of it, they're really different species now. And so we can, if we wanted to, we can model very different occupation fractions or scatters in low mass halos with no trouble. The data sets that we're using only go down to about 10⁻⁷ in stellar mass, which is large enough that we expect every halo to host the galaxy. But there's no trouble if we want in the future to have less than unity occupation fractions for low mass halos if we then were to combine that data. So.
Okay, last question.
Yes. Peter, could I ask what the prospects are for future additional parameters like sizes and versus concentration and ellipticities and things like that?